Hello and welcome to the sixth session of David Auerbach's 5 Paradigms of Artificial Intelligence from Leibniz to Google. David, please.
Hi, welcome back. We've got 3 sessions left, including today. I'm going to try to charge through stuff as quickly as I can while bringing out the salient points. I think most people have given me their paper topics, and I think we have most presentations sorted out. If for some reason I've missed anyone, please tell me as soon as please email me as soon as possible. And we may have, I think we're going to have a guest speaker somewhere in the middle of today who is a machine learning expert, and she should be joining momentarily, and I'll introduce her when she gets here. But first, we're going to sort of be going back and forth between symbolic AI and connectionism, or parallel distributed processing, as it's called today, and sort of seeing how there's a back and forth going on even at the time of the AI winter. And the AI winter is something that was defined very much in terms of symbolic AI specifically, because symbolic AI by the 1970s has been the dominant game in town for almost 20 years. And Minsky, McCarthy, Newell, and Simon in 1956 are trying to show that something approximating human thought can be created on the computer, because the computer is now available not just to the ultra elite in the military, but to companies and universities. And Moore's law, which says that the number of transistors on an integrated circuit tends to double every 12 to 24 months, has been ensuring that computer power has been doubling every year or two as well. So we're now at 1973, and James Lighthill in the UK writes his report saying that the promises of the symbolic AI people are simply not realistic. And the response from the symbolic AI people amounts to just please wait a little longer, because they see the computer power increasing exponentially and they think they're within spitting distance. And Lighthill doesn't see it this way. He thinks that it's not going to happen. And that's sort of where we are historically. And Lauren, my friend Lauren Moos, a machine learning expert, is going to be speaking about machine learning and perceptrons a bit. Lauren, I'll cue you when I think it's a good spot, and you can sort of conduct things however you want. And William, you're up for Eliza in a bit? Okay, you're sideways, by the way. That's okay? Okay, I guess you can present sideways. That's okay. All right. Even better. Okay. So, yeah, and Eric's going to speak a little about this McCarthy paper. This is McCarthy's 1969 paper, Some Philosophical Problems from the Standpoint of Artificial Intelligence. And McCarthy is extending the logicism we have already saying that his goal is formalizing concepts of causality, ability, and knowledge. And this is very much an extension of what he was proposing in 1956, and very much in line with Simon and Newell's physical symbol systems hypothesis, which, if you recall, maintains that the necessary and sufficient conditions for human thinking, for intelligent action, are being embodied a physical system that can manipulate abstract representational symbols, and that these symbols must inevitably be representable in formal logic. And Eric, would you like to? I have a few comments on the McCarthy paper, but Eric, why don't you start?
You can start. You can also start if you. I don't have that.
Okay,
how you want.
I'm basically, because we're a little behind, I'm going a little quickly. So basically in this paper, McCarthy is joining AI very explicitly with trends in analytic philosophy at the time, and in particular with the trends in analytic metaphysics that were being staked out by Saul Kripke and Ruth Barkin Marcus. And these trends orient around counterfactual statements being regimented in logic using modal semantics, or what are thought of as possible worlds. And the great appeal to the AI people is, isn't this a great way to plan out problem solving if we can think about possible worlds in formal logic and say, well, if program were to do this, what would happen? So that's the appeal of this modal logic and counterfactuals here. So McCarthy is suggesting that human reasoning and therefore computer reasoning can be represented in formal logic through representation of necessary and possible truths, which refer to necessary truths are true in all possible worlds, and possible truths are true in only some worlds. And this was a huge boom in analytic philosophy for several decades, and McCarthy's sort of catching it at its inception before it would hit the big time in the 70s. The details are not as relevant as just the broader point that human reasoning can be abstracted away from both the details of its implementation in neural circuitry, as well as from the pragmatic particulars of individual situations. And that second one is important because if all the pragmatic particulars really do need to be represented in formal reasoning to address any situation, the size of the logical representations is going to get out of hand very quickly. And that's one of the points that Lighthill makes. And I think, Eric, now I think I'll turn it over to you.
Okay, so what I found very interesting was that it seemed, as especially in the first part, of the paper, that somehow AI research and the question of, okay, what are the necessary and the sufficient conditions of AI seem to fuse with philosophy and with philosophy of mind and epistemology, and yeah, how can one know, and that there is no real distinction from an AI and a human mind. And this was really what was the most interesting point for me. They also enumerate a couple of questions which they say, okay, they need to be answered, or one need at least to look for an answer to them when we want to develop AI and when we want to learn about AI, and that one cannot ditch these questions. And there is this one, I don't know which page, yeah, on page 6, there is this one interesting remark about that there would be one possible way of ditching these questions, these philosophical questions about representation, about the possibility of knowledge and so on, and try to get an AI, so to develop an AI without answering these questions. And they say, okay, one would have to make a computer simulation of natural selection and try to see, okay, one has to, that several computer programs mutate in the simulation, and in the end, what is selected and what comes out of it is artificial intelligence. But the problem, so there we don't understand how does cognition, cognition work there, and we don't understand what is actually going on in the program that is selected out of this simulation, and that this, if transposed into reality, could be very dangerous. That, okay, an AI is created that we don't really understand. And this is the only way how to bypass these philosophical questions, according to the authors. And this is, but they say, okay, in practical research, this wasn't really successful, and therefore they won't try to. First of all, it's dangerous in practice, and it wasn't successful, and therefore they don't go this way.
Yeah, it's an interesting point you raise, because I think one thing I don't quite hit on is that there is a fear of, well, what happens when if we don't have complete insight into this, that one of the great appeals of symbolic AI is that it may make tons of mistakes, but you at least know exactly where the mistake is being made. And if you look at the dominant AIs we have right now, that's definitely not the case. They're quite opaque, which is why there's been sort of a boomlet in the idea of explicable AI or transparent AI or something like that. For my own sense is that it's a bit of a quixotic project, but we'll get to that later. Thank you, Eric. I'm only going to gloss over Dreyfus's critique, which is worth reading because certainly it's had a his approach has had its own sort of cottage industry, especially because people like John Hodgland were students of his and have extended that. But a lot of the people in AI proper, I think, didn't pay a lot of attention to it. Dreyfus was sort of a lone voice before Lighthill. I think a lot of that was he happened to be at the Rand Institute in the 60s with Simon and Newell and all those folks. And he came up with this Heideggerian rejection of the basis of AI, not just symbolic AI, but AI more generally. And as I said last week, I think that by turning it into an ontological argument, he may have actually caused the symbolic AI people set in their ways, because if you reject Dreyfus's ontological distinction between logically representable knowledge and some kind of amorphous background knowledge or know-how that eludes this representation and makes it impossible for machines to behave with true intelligence, if you don't accept that distinction, then Dreyfus's argument gets defanged. He drew it out of Heidegger's Being in Time, and that was also not something that made his argument particularly appealing to his colleagues. But there is an interesting parallel to Dreyfus's argument that we'll see later. So keep in mind that the note that Dreyfus tried to strike an ontological argument against AI. So while we're, I want to, but even with a more incremental critique of something like Lighthill, the symbolic AI response then is just, we're getting there, we just need more time and a bit more computing power, and we're getting computers so fast that we're going to be there soon. So you could also look at this from the fatalistic sociological perspective, that, as I said in the first session, science, the quote, science progresses one funeral at a time, or more accurately, one research grant at a time. And to stay in the 60s, I now want to do the heart of things by looking at two case studies of symbolic and non-symbolic AI. And we're doing this after the Lighthill reports that I want to contextualize sort of in the context of having these growing doubts about symbolic AI that haven't quite burst forward yet, but definitely the sense that, well, maybe we should have gotten more results by now. And ELIZA, which is this program in the mid-60s by MIT's Joseph Weizenbaum, that was named after Eliza Doolittle in George Bernard Shaw's Pygmalion. It was created, and one could say it is something of a joke, or at least the prototype of a joke. And I'm going to turn it over to William right now to present on ELIZA. William? I don't think we can hear you.
Yeah, the problem is my, do you hear me now?
Yep.
My computer camera is broken, so I have to use my phone for that. But I'm going to share my screen here. Is this working? Oh dear. Okay. Okay. Great. So let's see. Hopefully this is useful. I'm going to just try to move quickly and just say right off the bat that I'm not going to try to say anything particularly interesting about this program. I'm going to try to refrain from the opinion that I have anything particularly interesting to say about the program or the sort of techniques, and sort of engage more with the possibility that I have something interesting to say about the sort of cultural aspects, particularly focusing on the sort of type of psychology that they're talking about here, and also just move through it pretty quickly. So there are three things that are sort of ringing for me in some of these discussions, and I just want to sort of frame what I've been thinking about recently. One is Ernan had a presentation in the Computing the Real class on Kant's spatial a priori, and the way that like figures regarding the way he's talking about maths and sort of numerical operations and triangles. And it's been a while since I've read that sort of Kant, but that sort of like irreducible spatiality of the way that Kant is thinking about sort of numbers is like stuck in my head for some reason. I'm also interested in like centering a psychological perspective on the way that we're thinking about culture in regards to technology. And then the third is that I'm interested in centering a psychological perspective on politics and media, because that's going along a lot, I think, with some of the diagnostic discussions of Trump, actually. So I think we're just going to quickly watch this wonderful piece of documentary on Weizenbaum. Let's see. That I found through an Adam Curtis essay, actually.
With via the keyboard.
Can you guys hear that?
And it'll reply on the screen. We've added human speech. Does it understand what it's doing in the sense that we do? Easily, for Eliza is a computer program that anyone can converse with via the keyboard, and it'll reply on the screen. We've added human speech. Section more clear.
Men are all alike.
In what way?
They're always bugging us about something or other.
Can you think of a specific example?
Well, my boyfriend made me come here.
Your boyfriend made you come here.
He says I'm depressed much of the time.
I'm sorry to hear that you're depressed.
True. I am unhappy.
Do you think coming here will help you not to be unhappy?
The computer's replies seem very understanding, but this program is merely triggered by certain phrases to come out with stock responses. Nevertheless, Weizenbaum's secretary fell under the spell of the machine.
I stood in my office and sat it down at the keyboard, and then she began to I looked over her shoulder to make sure that everything was operating properly. After 2 or 3 interchanges with the machine, she turned to me and she said, "Would you mind leaving the room, please?"
And yet she knew, as Weizenbaum did, that Eliza didn't understand a single word that was being typed in.
You're like my father in some ways.
Okay, so I just want to stop there. Just to frame this by saying that clearly there's a lot going on from any sort of reading, but I mean, at least we can situate this within some sort of at least earnest belief or attempt in some sort of psychotherapeutic properties here, both from Weizenbaum and from his ingénue assistant. And I think that's interesting. This is the machine that it was built on, IBM 7094. I'm sure David, well, actually, David, I don't know how old you are, but you might remember this. I don't know.
No, I'm not that old.
Okay, yeah, it looks pretty ridiculous. Yeah, but this, I think, just gives us a sense for what programming was at this moment. There is no GUI. It's just the idea of computing, and particularly human-computer interaction, I think this can remind us that it was just very different at this time. And then I also just want to point this out because I think this is I know it's important for programming, even from my sort of sophomore understanding of it, but they discuss the kind of idea of a pointer. In computer science, a pointer is a programming language object that stores a memory address. This can be that of another value located in computer memory, or in some cases that of memory mapped computer hardware. So there is this, and this might actually not be an accurate description of the pointer that is going on at the time, but I think this is sort of an important way to sort of think about both the mental process of programming that's going on for Weizenbaum and also the sort of like structure of the machine in any sort of more ambitious ways that we can try to frame what's going on, whether we're thinking about the sort of, basically, if we want to think about spatiotemporality in the context of the machine, I think this is at least like the bare minimum of thinking about it in the terms of sort of the idea of a pointer. And I don't know enough to describe more, but I think that, all of us can, probably many of us have, but the rest of us could do a very good job by looking more extensively at that. So, and then again, I'm not going to go into actually how this sort of paper is actually functioning, but as anyone who takes a quick look at it can see, it's basically composed of these sort of rules. It's a rule-based machine that's trying to get us some natural language processing, and it goes, it takes keywords out of user input, and then it goes through this process of decomposition rules, reassembly rules, and then there's sort of this interesting sort of process of memory rules, where it sort of accompanies the sort of decomposition reassembly process with sort of shortcuts here and there. So yeah, I'm not going to try to get into that. But the sort of definition at the end is that seen in the coldest possible light, ELIZA is a translating processor in Gorn's sense. However, it is one which has been especially constructed to work well with natural language text. And then here, looking at this the definition from Gorn, given a language which already possesses semantic content, a translating processor, even if it operates only syntactically, it generates corresponding expressions of another language to which we can attribute as meanings the semantic intents of the generating source expressions. Whether we find the result consistent or useful or both is, of course, another problem. It is quite possible that by this method, the same syntactic object language can be usefully assigned multiple meanings for each expression. This is the definition that they give the system, and I think it's a useful definition, particularly in this last point of it is quite possible that by this method, the same syntactic object language can be usefully assigned multiple meanings for each expression. I think it's useful to keep that sort of definition in mind and that sort of problematic in mind. It seems like there's some sort of like, the way that they're situating this theoretically is like a mapping from a certain idea of what meaning is, or sort of perception of meaning from the human onto some sort of semantic utility that's going on in the machine. And this, I think, is quite interesting given the sort of overall culture of the 1960s, the late 1960s. We talked a little bit about Pynchon, but I think this background's an interesting discussion of the sort of psychological ambiguities that we see in the literature of this time, particularly in Pynchon. Yeah, so I'm trying not to be too ambitious in the way that I'm reading this. But that, I think, is too there to ignore. Now, I am going to make one quick note, is that I think we'll probably talk about this, maybe we already have, about the sort of import of GPUs to the way that deep learning is working, the way AI is working today, as I understand it, and the sort of idea of parallel processing. And David, you might comment on this after, but it's just my intuition that the sort of sequential type of programming and sort of processing that they discuss in this paper is really quite different from any discussion of sort of parallel processing. That's just an intuition. Now, I also want to say that so in 1960, or this paper was written in like 1965, 1966, and it is, of course, sort of composed discussing a lot of psychology. This is also during a time when Alfred Hitchcock was in his peak years. This is obviously still from Psycho in 1960. There was sort of a cultural stigma around therapy, particularly around the idea of psychoanalysis. This paper is not engaged with psychoanalysis. It was engaged, I think, with reversion psychotherapy or something like this, which is more aligned with the sort of call and response that ELIZA actually identifies. And I think that's why David introduced this as a sort of joke, because it's so unbelievably, the program is apparently so unbelievably simple, but it does it by using this sort of language game that reflects a certain type of therapy, whereby the sort of therapist just sort of echoes whatever you say. So you say, I'm upset at my dad, and the the machine can sort of through some sort of rule-based system can say, tell me about your dad. And the sort of hitch to this whole process is that the machine doesn't actually have to have any knowledge of the real world. It can just use this sort of like echoing inferential process to appear as if it knows about the world. And what's interesting, and the reason why I started with that original video, is that there is actually some sort of psychotherapeutic effect, at least it seems, in this process. I also want to point out that this is a little bit different from, of course, this psychology is obviously a massive field, but it's different. This is a different model of sort of idea of sort of transitional, sort of interior to exterior relationship that's going on in something like psychoanalysis, for instance, in which the sort of relationship between a person's psyche and the outside world is mediated by sort of objects and sort of sensible phenomena. I just want to frame that for anyone that's interested in this sort of essay. I think it's quite useful. And then lastly, to end, I just want to do, very quickly, I want to do just a bit of a close reading, because I'm willing to advocate for the utility of close readings of these texts. And we can argue about that at some point after class or whatever. But so I want to talk about this, this quote here, because I think it's very interesting. This is on page 6 or so, although the page numbers are a little confusing. How must the script be written in order to maintain the credibility of this idea? And by this idea, I think it means the sentience or the sort of understanding nature of the machine. But how must the script be written in order to maintain the credibility of this idea over a long period of time? This, I think, is a sort of an interesting question, and it's an interesting moment within the essay. And now I just want to turn to page 9. If possible, and I'd love for us to read along with this, and I just want to point out my sort of own notations of this page. Let's see. Yeah, okay. So, and y'all can note my notations, whoever you'd like. Yeah, there's just so much going on in this paper. It's like, it's hard to sort of summarize in any way, particularly if I'm, not going to make the attempt to pay attention to the program, but let's just go through this. So a large part of whatever elegance may be credited to Eliza lies in the fact that Eliza maintains the illusion of understanding with so little machinery. But there are bounds on the extendability of Eliza's understanding power, which are a function of the Eliza program itself and not a function of any script it may be given. The crucial test of understanding, as every teacher should know, is not the subject's ability to continue a conversation, but to draw valid conclusion from what is being told. In order for a computer program to be able to do that, it must at least have the capacity to store selected parts of its inputs. Eliza throws away each of its inputs except for those few transformed by means of the memory machinery. Of course, the problem is more than one of storage. A great part of it is, in fact, subsumed under the word selected used just above. Eliza, in its use so far, has had as one of its principal objectives the concealment of its lack of understanding, but to encourage its conversational partner to offer inputs from which it can select remedial information, it must reveal its misunderstanding. A switch of objectives from the concealment to the revolution of misunderstanding is seen as a precondition to making an Eliza-like program the basis for an effective natural language machine communication system. One goal for an augmented Eliza program is thus a system which already has access to a store of information about some aspects of the real world, and which, by means of conversational interaction with people, can reveal both what it knows, i.e. behaves as an information retrieval system, and where its knowledge ends and needs to be augmented. Hopefully, the augmentation of its knowledge will also be a direct consequence of its conversational experience. It is precisely the prospect that such a program will converse with many people and learn something from each of them, which leads to the hope that it will prove an interesting and even useful conversational partner. One way to state a slightly different intermediate goal is to say that Eliza should be given the power to slowly build a model of the subject conversing with it. If the subject mentions that he is not married, for example, and later speaks of his wife, then Eliza should be able to make the tentative inference that he is either a widower or divorced. Of course, he could simply be confused. In the long run, Eliza should be able to build up a belief structure, to use Abelson's phrase, of the subject, and on that basis detect the subject's rationalizations, contradictions, etc. Conversations with such an Eliza would often turn into arguments. Important steps in the realization of these goals have already been taken. Abelson is interesting, like kind of really interesting, actually, and I'm not going to go into that, but I want to say that this particular page, and the whole essay certainly, but this particular page references a certain ambition by these authors to not only sort of create the sustained illusion of understanding, typical of some sort of, something that could pass some sort of Turing test, but also an ambition to sort of move forward and to create a system that already has access to a store of information about some aspects of the real world. And I think this is some sort of ambition towards something that we could call data. And that is, there's obviously conjecture around that, but I just want to focus very specifically that one way to state a slightly different intermediate goal is to say that Eliza should be given the power to slowly build a model of the subject conversing with it. And the way that they pose this, in the way that Eliza should be given the power to slowly build a model of the subject conversing with it, is through this work of Abelson. So if we want to look particularly at the psychological model that they're underpinning this intermediate goal of the ability of Eliza to sort of build a model of the subject that is conversing with it, we can look at that sort of psychological paradigm and the way that that's situated as they're writing this. And there's already, it's sort of easy to do that, actually. Abelson is an interesting character who is hugely influential, was at the Macy conference, and it makes this machine called the Goldwater machine, which is able to, it's a machine that is able to sort of simulate the personality and behavioral responses of, what's his name, something Goldwater, who's the conservative politician. So there's actually, I'll send along a link of a marginally interesting article of people talking about Abelson in the context of AI, and actually in the context of Eliza. So yeah, thank you.
Great, thanks, William.
Sure.
I wanted to pick up in particular on your use of the term language game, because on the one hand, it very much does seem that this is exactly what's going on. That this is a wait, I'm spotlighted. Why do I still have? For some reason, I still have William's screen. Is everybody else? Okay, there we go. Great. Okay, language game. That does very much what Weizenbaum describes does seem like a game very much, and yet, at least in the sense of a Wittgensteinian language game, Wittgenstein would insist that Eliza is not playing a language game because it's not able to perform improvisatory or creative actions that within the game that at least the human user thinks is being played. So I think it really there's an interesting notion raised by this, which is to what degree can someone pretend to play language game? And there's a lot in Wittgenstein that speaks to this that it would be great to get into at some point or another.
I had one question. I had forgotten that I wanted to just end with this. Oh. Do y'all hear me?
Yep.
Okay, thank you. I had forgotten that I wanted to mention this. But there's a certain moment in the text where they sort of discuss language as like there seems to be a certain like privileging of language as not necessarily of the world in a certain sense, and maybe I'm reading it wrong, but it seems like a certain privileging of language as like a particular, and you might have just contested that in what you just said, David, but there's a certain, let's see if I can say this quickly. yeah, I can't really remember exactly what it was, but it's something about how it seems in this, that Weizenbaum is sort of talking about language in this sort of maybe like essentialist way that doesn't really make it feel like language is sort of the world. And I was wondering if this sort of we can think about this in the way that we've been discussing functionalism for a couple of classes.
Yeah, I'll be speaking to that. I think Weizenbaum is actually probably more conscious of that than say Simon or Newell is. But what I think he wants to get at the fact that certain grammatical structures can be isolated, independent of context, and basically the things that are of the world, he is trying to factor out as best he can, because those are the most problematic points. So Weizenbaum, he's a bit more of a nonconformist than the strictly symbolic AI people. Somewhat akin to Wiener, although not as extreme. He doesn't trust the government or the military. He's weary of the computer revolution as a means of mechanizing and standardizing everything. And it's possible that his many years when he was working at GE may have helped foster that attitude in him. Based on my experience in corporations, I would certainly be inclined to think that they would have that effect. ELIZA is intended as something of a toy program that is a bit of a parody of what William said, a non-Freudian psychotherapy at the time by Carl Rogers. Rogerian therapy is also termed client-centered therapy, and it's often caricatured as being therapy in which the therapist doesn't actually have to do much other than nod, repeat what the client says, and say, how does that make you feel? It's much more hands-off than psychodynamic therapy in that regard. So he creates this program to act something like a Rogerian therapist in the simplest of ways. And his purpose is to indicate that there is a bias with regard to the opacity of computers, that we have a bias. And he says, once a particular program is unmasked, once its inner workings are explained in a language sufficiently plain to induce understanding, its magic crumbles away. It stands revealed as a mere collection of procedures, each quite comprehensible. Weizenbaum was apparently stunned by just how seriously people took ELIZA and believed that ELIZA understood them or was doing something other than what it was actually doing. Because Weizenbaum's project is in some sense an inversion of Simon and Newell's. Rather than trying to lift computers up to a point of actual thinking, Weizenbaum sets out to write a program that he believes is not doing any thinking, and then explains why people might believe otherwise, why people might believe that it is in fact thinking. So there are two critiques in play here. The first is that in a sufficiently restricted environment, whether it's the logic solver of GPS or the Rogerian therapy of ELIZA, or the very short messages of Twitter, I would say, behavioral assessments can be tricky to make. There wasn't an easy way to tell if Simon and Newell's human actually was thinking in the same way as GPS, just because the protocol matched up with the program trace. But Simon and Newell took it as an indicator that the two did have similar thought processes. Similarly, if you were to have a Rogerian therapist who spoke similarly to ELIZA in some session, would that be an indication that ELIZA was thinking similarly? Well, obviously not, says Weizenbaum, because ELIZA is, from an examination of its algorithms, extremely stupid. It knows almost nothing about syntax because it doesn't break down its inputs grammatically or construct its outputs grammatically. It merely has a list of keywords that it knows to ignore, which are the various function words of English, and has a few replacement rules, such as swapping out you and I, so that when it embeds the user's phrases in its own replies, ELIZA keeps the reference correct. And we saw this in some of the transcript, in the video that was being shown, where you know, you say you say, let's see, I'm unhappy, and says, oh, do you think coming here will help you not to be unhappy? It's simple. And what we saw is actually better than usual. It's not hard to get ELIZA into a mess because it often misreads grammatical sentences and injects fragments of them inappropriately into its responses. And later that, ELIZA knows nothing about semantics because its processes involve pulling keywords out of sentences, or keywords or phrases out of sentences given to it by its users, and then spitting them back by inserting them into potted English sentences. It's not using formal logic, but this process could certainly be modeled using formal logic. That implies that Simon and Newell's physical symbol systems hypothesis, and specifically their contention that the manipulation of symbols is sufficient for human thinking, suddenly seems dubious. Because the way I read the physical symbol systems hypothesis, there's no guideline by which we can say that Eliza isn't doing some form of thinking, at least at a very primitive level. But the other critique, and I think ultimately the more far-reaching one, is one that harkens back to the Turing test criteria, because Weizenbaum is suggesting that humans can be truly terrible judges of what constitutes thinking. The way I read it, Weizenbaum unintentionally echoes the cyberneticist desire to put the concept of thinking posterior to the question of organism and environment, because Weizenbaum calls into question not just the ability of a human to assess how smart a program is, but the ability to assess how smart anything or anyone is. The critique of Eliza is one of saying that the mystic aura around a program can easily dazzle someone into attributing all sorts of false thoughts to it. And moreover, Weizenbaum hints that artificial intelligence as a term may in fact be self-defeating, because if thinking is not this absolute thing that can be captured by a definition such as the physical symbol systems hypothesis, then AI will get sucked into a pattern of imitations of thinking, and we ourselves will ultimately not be able to judge whether or not the program is thinking or not even people like Newell or Simon. I think this is almost a Pyrrhonist move by Weizenbaum, a way of saying that the focus on thinking is ultimately a trap that reifies our own blind spots and puts us, to use a Wittgensteinian analogy, into the position of thinking we have a yardstick with which to measure thinking, when in fact we have no way of assessing whether our yardstick's markings are correct. Or more to the point, if two people have yardsticks with different markings on them, we don't have any way of figuring out which markings are correct, other than arguing until one person gives up and the other wins. And to put this in terms of symbolic AI, we could say that even given a successful protocol trace in a larger context, where a machine manages to mimic a human's problem solving on a trickier and more context-dependent problem, that very judgment of success is going to be conditioned by all sorts of human biases. The symbolic AI thinkers believe they found a point of reference by appealing to formal logic as the ultimate arbiter of how thinking works. But that's a tenet of faith rather than a provable statement, because you have to believe first in the logical structure of reality, then in the logical structure of thinking, and third in the correspondence between the two. And that is in no way established. Rather, that's a contention of people with a certain yardstick. So Weizenbaum is placing the emphasis back on the problem of the human judge, which again echoes the cybernetician's concerns about the anthropocentricity of words such as thinking, mind, reasoning, and the like. And I think Turing actually offers some insights here that are overlooked or as a way around this impasse, at least partly. Turing contended that it was the act of fooling humans in a socially embedded setting that should replace any other criteria for thinking. And what Weizenbaum illuminates criteria stands against both the cyberneticians and the symbolic AI group. On the one hand, he wishes to make humans the measure of thinking because Turing believes the term is sufficiently important to demand a definition or at least a criteria. He doesn't want to place thinking anterior or posterior to ecological environments and organisms. On the other hand, Turing wants to be functional about the definition of thinking in a relativistic way. Turing realizes that thinking is a culturally embedded term, and so he establishes his own black box criteria for what constitutes thinking at a given point in time. Because while Eliza dazzled people in the 1960s, particularly those who had no idea what it was doing, Eliza seems less impressive today. On the other hand, Siri and Alexa can seem uncannily human to people at times, even though they're ultimately just updates of the same tricks that Eliza pulled, drawing on a more sophisticated set of rules, heuristics, deep learning techniques, and the use of voice synthesis and voice recognition to interact in a modality not traditionally associated with computers. So the Turing test is in fact adaptable, because passing the test at one point in time, I'm not saying Eliza did, just that passing it with sufficiently naive judges would have been easier in the 1960s than it would be now. Doesn't guarantee that you pass it in the future. Turing embraces an anthropocentricity in terms of subjectivity rather than in terms of rationality. Weizenbaum's conclusion, which is a bit more modest, is something similar to what Lighthill would say about almost 10 years later, that AI is a field focused not on the lofty problems of simulating human thought, but on creating tools with which to assist human problem solving. He says towards the end, this appears to be the best way to use a truly interactive man-machine facility. not as a device for rapidly debugging a code representing a fully thought out solution to a problem, but rather as an aid for the exploration of problem-solving strategies. His conclusion is that yes, computers and these AI problems will be mechanistic, programs will be mechanistic, but their particular strengths can serve as cyborg-like additions to human thought. And symbolic AI's work in developing expert systems, the programs that work within one specific domain and use heuristics, probability, and logic to reason about problems within that domain, bears out Weizenbaum's conclusion. The symbolic AI people hoped for more and promised more, but Weizenbaum's limitations seem to hold sway for at least some time. And I would argue that for symbolic AI methods, they still hold true today. And moving forward, Drew McDermott in 1976 makes Weizenbaum's implicit critique far more explicit. This is the paper, what was it? Artificial Intelligence Meets Human Stupidity. When he says that, he effectively says, yes, Newell and Simon's general problem solver is really just an extension of ELIZA. And he does so by making an inverted Turing argument, by saying that the language in play has disguised how rote and simple the operations are. McDermott explicitly says that the terms in play have greatly inflated the abilities, that having programs that specify things like goal, theorem, and provide an ELIZA-like illusion of sophistication that when in fact they are no more sophisticated than primitives like if needed or add. McDermott says that concepts of intelligence have been smuggled into systems like GPS in a case of theft over honest toil, which is Bertrand Russell's old phrase. And McDermott puts this by saying that a semantic network is not semantic. In other words, just because you have words linked to other words via words denoting relationships between those words, that does not mean that the possessor of this semantic network has understanding of those words and relationships. This seems like a fairly obvious point from our perspective, I take it. And so it may seem to be surprising that McDermott takes such pains to make it. He points out, just like Weizenbaum had, that human language is very slippery in terms of the degree to which we judge its performance to have meaning. This is on page 6. The obsession with natural language seems to have caused the feeling that the human use of language is a royal road to the cognitive psyche. I find this analogous to preoccupation with imagery as a way of studying vision. Most AI researchers react with amusement to proposals to explain vision in terms of stored images, reducing the physical eye to the mind's eye. But many of the same people notice themselves talking to themselves in English, conclude that English is very close to the language of thought. And the interesting thing here is that, weren't we using formal logic, and that was the language of thought rather than English? That seems to be what the contention of the physical symbol systems hypothesis is, and why GPS started off with formal logic problems. And yet here McDermott is saying that AI has developed a problem of regimenting natural language as the conceptual language of thought rather than logic. The irony being, of course, that this language must be then turned into a formal logic representation before a computer can deal with it. So there are 3 levels in play: the level of the language of natural communication like English, the language of computational representations, which is formal logic and mathematics, and the language of thought, about which we know very little. And to elaborate on McDermott, the thinking process here seems to have gone as follows. 1, humans think in some sort of abstract, unified way. 2, they express themselves in natural language. 3, that natural language must be close to what thinking is. 4, thinking must involve the formalized manipulation of symbols by the physical symbol systems hypothesis. 5, any physical symbol systems hypothesis can think. And therefore 6, computers should be able to use natural language rather easily. And that's how one can construct a rejoinder to Weizenbaum, by lumping logic, language, and thought into one category and seeing them as more or less equivalent, as well as, of course, seeing them as having a metaphysically significant parallel to reality. And this is way further than the Vienna Circle ever went. And I suspect it's because of the technological limitations that they were addressing, because the symbolic AI people were not just theorizing, but wanted to get programs working. These philosophical shortcuts consequently became immensely appealing to them, just as behavioralism and functionalism had seemed attractive shortcuts in human psychology. You celebrate what you have and you denigrate the importance of what you don't. And so even 17 years later, even after symbolic AI has lost much of its luster, McDermott seems equally exasperated with the arch-symbolic psych project, CYC, whose goal was a generalized base of knowledge in which engineers were just feeding logical fact and after logical fact into a large store, such as all cats have 4 legs. Psych then uses logical formalisms and inference rules to draw new facts from the original facts, like cats have more than 3 legs. but then it runs into problems if you have a cat with an amputated leg. And McDermott stresses that. He says, this is the later McDermott paper, the review of building large knowledge-based systems. Is the content problem is even that when you can state a large piece of knowledge that psych ought to know, you can't necessarily express it in a formal language. If you express it any old way, then eventually some algorithm in the system is going to draw conclusions from it that don't make sense. For example, in section 6242, the authors discuss representing Fred works as a plumber. The straightforward way of representing this proposition would neglect time and yield inferences such as, for 9 months before Fred was born, his mother carried a plumber. And I mean, my moment, I think, of disenchantment was in the wake of September 11th. The head of the psych program was saying that psych had managed to predict that terrorists might attack America using crop dusting planes with anthrax. And technically speaking, that's true, but the problem is that it had predicted, that was one of many, many, many predictions, including the prediction that dolphins would attack Hoover Dam carrying bombs. And so, you know, there's the element of cherry picking that you get, yes, you can get things that look good, but how is that different from Eliza producing something that looks good? And that's McDermott's point. And consequently, McDermott is entirely dismissive of psych as a way to get to generalized AI. And in fact, thinks generalized AI isn't even a goal worth pursuing. But if McDermott is right that there seems to be no general knowledge representation scheme that actually works, whether it's formal logic or anything else, then what's left? How on earth do we represent knowledge if we can't even come up with a generalized schema in which to do it, which computers can understand? What is this thing called human language that seems detached from logic and perhaps also from thought? Or even better, what is thought? So you lean towards this mysticism around the human mind and human communication. It's understandable that a more optimistic person might be frustrated by McDermott's seeming Pyrrhonism. And yet the results have been incredibly poor. So the question I want to pose as we move towards connectionism is what does it mean for AI as a field to set aside the question of thought and communication? We have seen the cyberneticians treat them as black boxes, but this move is going to be slightly different because rather than abstracting over thought in language, we're now treating them as something beyond, something almost godly in the Leibnizian sense. So in other words, if AI is going to remain in this human realm, which is where we have the most problems that we want it to solve, what we will have to do is not abstract over thought in language, but we'll have to work around it. And I suspect that, you know, the resistance to that sort of Pyrrhonism may have, you know, increased symbolic AI's appeal. Why fiddle around with neurons and symbolic representations if thought itself is within your grasp? And this argument played itself in practical terms as well as theoretical ones, and this is where the perceptrons controversy comes in. And there's still a great deal of debate over what constituted the controversy and whether there even was a controversy. But at the heart of it, you have a post-cybernetic approach by Frank Rosenblatt to a non-feedback model called the perceptron. And the lack of feedback is significant here, since introducing feedback later changes the landscape significantly. And this approach suggests a larger non-symbolic, non-cognitive approach to AI. And the symbolic AI thinkers react strongly against it, particularly Minsky. And so to this end, we're going to look at a bit of Frank Rosenblatt's 1962 book. What is the name of the book? God, what is the name of Rosenblatt's book? Where did it go? Principles of Neurodynamics, right. Rosenblatt is at Cornell rather than MIT, and he died quite young in 1969, I think, which did not help perceptron research. He too was rather to the left and less warm with the military-industrial complex than some of the symbolic AI people. And I don't want to overplay that divide or make it out to be that one side was pro-military and one anti, but I do think that we can say the cyberneticians and Rosenblatt were on the whole a bit more colorful characters than the symbolic AI wants, and perhaps less cozy with with the Defense Department. So, and what Rosenblatt comes up with here is really the beginning of neural networks and machine learning and ultimately of deep learning. And what a perceptron is what boils down to it, a binary classifier. He has an idea of a network of these nodes which take inputs that are to be classified in one of two ways. Is this text in English or not? Is this email spam or not? Is this a picture of a tank or not? And so on and so forth. And I guess here I'm going to let our esteemed expert take over and speak for a bit. Lauren, are you up for this?
Yes, I absolutely am.
Okay.
I am going to speak for a while, but then I'll stop. And if anyone has questions, I don't know if some of you are curious about like the more quotidian aspects of machine learning, but I want to like give some space and time for that.
Lauren, do you want to say what it is that you do and what?
Sure.
Yeah.
So I'm a machine learning researcher and engineer. I have like an unusually eclectic background. I've done some work in deep learning, but I've also done some work in Bayesian models, and then unsupervised learning, which is like learning without ground truth. But
that's not possible according to Minsky.
It actually turns out that it is, and it is with techniques that are quite.
What?
Yeah. And I think there's been like a recent resurgence of interest in unsupervised techniques just because there's like a relative absence of labeled data. So there's a relative absence of data where you have email classified as spam or not spam. Like most real world problems aren't that closed. And so if the problem isn't closed, it's unlikely that there's a lot of observed clean data that has labels that can be trusted. So I also will speak a little bit, I want to focus, like I'll go a little bit over like model architecture and some of like the math at a very high level, but I also want to go over some of the like big epistemological like assumptions that go into sub-symbolic AI and deep learning. I think that like the perceptron isn't quite as much of a leap in logic if you accept the fact of something called thought vectors. I'm going to read this quote because I think it's very interesting. And I think that this, when you read introductions to deep learning, this assumption, this critical assumption of deep learning doesn't get a lot of airtime. And it's actually, I think it's probably one of the most philosophically difficult things to accept. And if it's right, then everything's right. If it's wrong, then everything's wrong. So I want to give some space to it. So it's a little bit long, so forgive me. But Hinton, who's the great grandfather of deep learning and probably one of the most intellectually honest people, he's very widely respected in the machine learning community, says that the implications of this for document processing are very important. If we convert a sentence into a vector being an array of numbers, so it represents some point in some dimensional space, that captures the meaning of the sentence, then Google can do much better searches. They can search based on what's being said in a document. Also, if you can convert each sentence in a document into a vector, then you could take that sequence of vectors and try to model natural reasoning. And this was something that old-fashioned AI or symbolic AI could never do. If we can read every English document on the web and turn each sentence into a thought vector, you've got plenty of data for training, like the previous speaker went over with Eliza, training that internal model, a system that can reason like people do. Now, you might not want it to reason like people do, but at least we can see what they would think. So basically, this is like the central problem, and it often gets erased in machine learning textbooks, which is that given a sentence or an image, if you could successfully translate that into a vector, then you could feed it into some model that applies some series of like linear and nonlinear transformations. You could learn from the error, and then you could incrementally correct the model until it learns more. But the critical step is that encoding step. Like, is it possible to take something as rich and recursive as human language and to represent it as a point, albeit a point in a very high dimensional space? I think it's like an open question, but there's been some very interesting work that's been done recently on this. So basically, like the most critical epistemological assumption of a multi-layer perceptron is that it accepts as its input a vector. And how that vector is constructed is done with a variety of methods called encoding methods. And I think it's interesting that people keep mentioning Wittgenstein, because it's actually a very Wittgensteinian idea, which is basically that, like, can you represent language so that if a sentence is similar to another sentence, that they lie close together in that space, and if it's dissimilar from another sentence, that they lie farther away. But even more than that, can you capture analogical reasoning through vector permutations like addition and subtraction? Like, could you model simple metaphors by the locations of these points? And if you think about it, it's a very non-Wittgensteinian way of representing language, because instead of figuring out the very difficult problem of semantics through hard coding like would be done in symbolic AI, it's almost learning it in the syntactic like way, where it's learning it as a series of relationships, of like contextual relationships of these words. And so once you like stomach that, and I think it's pretty easy to think of an image being reduced to a vector. There's like simple mathematical operations you could do to do that, but I think it's much more difficult to think of a thought vector or human language as a vector. But what a multi-layer perceptron basically is that, so given this like binary classification task, while I'm explaining this architecture, I want you to imagine, imagine a graph like in school, and then imagine two clusters of points. One cluster of points is red and one cluster of points is blue, right? And so there's a cluster of points that are spam and a cluster of points that aren't spam. But at this point, we don't know how to discriminate between those two. So what we want to learn, right, is a line called the decision boundary that separates these two clusters. And this is this very lucky case where the clusters are linearly separable, which only, like, it's very simple what that means. It just means that you can draw a line that cleanly separates the two different categories of points. So what happens is you have an instance of an email, and you know what it is. You know if it's spam or not spam. And so then you do a forward pass through the network, and depending on whether or not you got the classification correct, you either update the model or you don't update the model. So that's constantly switching this line in space, this line being represented by the model weights, until you finally get this line that is, you know, it reaches whatever accuracy threshold you want. What David alluded to is the important innovation with that is it's called differential contribution of error. With an email, there might be multiple features that make it spam, like using certain like simple language, or saying that you have a bank account in some foreign country, or certain things might characterize whether or not that email is spam. And so that would be encoded somehow in this vector that's entering the model. And so if you reach the end of the model and you've made an incorrect guess, the model thought it was not spam and it is spam, you want to know what features to incrementally adjust, what weights of the model need to change, so as to take into account the variable importance of different features in the vector that you fed it. And so that was a development that happened later by Geoffrey Hinton, and that was one of the big things that sort of unleashed the power of deep learning, that it just an increase in raw computation power. Because you could imagine that you could only do very crude adjustments if you don't know how to sort of tease out what exactly is causing you to make mistakes in the model. And one of the interesting things about like the multi-layer perceptron, if you look at modern day deep learning, is extremely like humble. It's a very, very simple set of transformations. But what makes it interesting is there's a theorem in computer science called the fundamental approximation theorem, which is that no matter how complicated that decision boundary is between those points, those red and blue points, let's say they're all like mixed together, as long as you have a hidden layer with a nonlinear activation in your perceptron with an arbitrary number of nodes in this graph that is the network, you will be able to approximate any decision boundary no matter how complex. And so that really was like very exciting to people in machine learning, because even though it's very theoretical and the amount of nodes to actually approximate the line might be infinite, it does mean that, you know, we found something, this idea of continuous differentiability, that's as essential as the logical proposition. So there's something like extremely like fundamental about this type of models. Like it expresses something mathematical that's like very, very big and broad. Theoretically, we should be able to discriminate between, you know, any arbitrary number of things. But what's interesting is this also relies on this theory of knowledge that is like this idea, epistemological cleaving kind of, where it's like you're not really knowing something innately, you're knowing that it's not all these other things that you're including in the data set. And like whether or not, I mean, that's how human beings know things, I think is dubious. Like I don't think that like I know that something is a lamp because it's not a table. I would say that in terms of like how I think about developmental psychology and like cognitive science, like there's something about these encodings, a step that happens prior to feeding into a machine learning model that's extremely interesting. So I moved to Paris and I'm learning French, and I'm in this class, and unfortunately everyone's like super advanced in this class and I'm not. And so everyone's speaking French really well. And I noticed that the key difference between me and them is that I still have this mapping between this is a French word and this is an English word. And that's how I've like added to my French vocabulary. Whereas they're able to say, oh, this French word's similar to this other French word, but it's different from this other French word. So it's that contextual understanding. And it really reminds me of this way that we have of encoding natural language in deep learning. And it's what I lack. And so I seem to lack understanding because I'm not doing that mapping. I'm instead doing something that's more like symbolic AI, where it's like an explicit mapping between like a word and its pair. It's not capturing that like embeddedness, like this like rich contextual embeddedness. And so it's much harder for me to negotiate. I would say with all this being said, you know, like sub-symbolic AI is a powerful tool. It's had a lot of like very obvious wins, especially in computer vision, which I worked in for a little bit. But there's been this real sort of nostalgia for symbolic AI because of the precise problem the symbolic AI people were having, which is how do you have something like a Kantian a priori? Like how do you have like a spatial temporal causal a priori? It's very difficult for a network to learn those sorts of relationships. It basically only learns correlations. It learns very complex correlations that are far more complex than you or I could learn, but it's not, there's nothing causal about it. I mean, the question is, can you learn causality just from seeing a bunch of examples of how causality works? And I think a lot of people are saying no. And so there's this need for this like Kantian a priori. And then related to that, but perhaps I would say like a layer up from that, there's no understanding of relational common sense, which they talk about in the Eliza paper. Like we're still struggling with these issues like 50 years later, like no one's figured out how to do it. And there isn't an obvious solution. And I think what we'll see in the next 5 years is an explosion of hybrid models. David worked at Google, so he's probably very familiar with hybrid models, where you have this matching of hybrid, like you have this matching of symbolic, rule-based, search-based systems with sub-symbolic systems. And like you get something from this sort of prior like model of the world. So you basically go from like Locke to Kant. Like instead of having something where it's complete, like blank slate, like everything is based off of this biological substrate, like everything could be learned from observation, you have something where you have kind of this warm start because you know simple rules, you know simple relationships, you've shared knowledge with other machine learning models. And it seems clear that like that's more common to how we learn. And I think the only reason why there was like 20 years where people like stopped talking about symbolic AI and didn't talk about these hybrid models was Hubert and Wiesel, who were two neuroscientists, saw in the cat retina that there were certain retinal cells that activated for highly specific edges. And it's like, oh, finally, we found this part of the brain that's like super computational. It's like, okay, so you just build up these simple edges hierarchically until you have like more complex shapes. And that's how we recognize objects. Like, that's great. That sounds like what computers do. And so this thing called convolutional neural networks, which like didn't happen too much later than the perceptron were generated. And instead of people spending all this painstaking time hand coding, like having to be like expert, you know, optical physicists and like early computer graphics people, there's no separation between computer vision and graphics initially. Like with something called feature engineering. So instead of having all this feature engineering, you could just have this network that seemed to be able to learn anything by like imitating these hierarchical, sort of like, imagine Tetris blocks being combined, and you just do that enough and you're able to create these like complex objects and images. So that was really exciting. And I think it was so exciting that it made people forget how little we were actually doing. Like that luckily was something you could easily put money on. Like a system that does that is like capable of producing value for a company. But because of actually like the collapse of the military funded research and the fact that it moved to private industry, people got really happy with what I think, you know, like Minsky would see as a very small win, you know, like it being able to do very, very specific tasks, albeit in a highly generalizable way. And they lost sight of these like grand projects of like, what if you could have a machine learning algorithm that read a text and you could just ask it open-ended questions and it would be able to respond in a plausible way? Or like, what if a robot saw an object like move around a bunch and like get covered with a towel and get uncovered with a towel and could still recognize itself as that object? Like, these are problems that they seem like they're the next incremental step in natural language processing and computer vision, but it's possible that the field will have to go through a whole paradigm shift to get there. It seems like we might asymptotically be approaching the end of what our existing models can do, and it's a big source of ongoing debate. And so if anyone has any questions, I'm happy to answer. I hope I wasn't too mathy, but regardless, if there's any questions, please.
So Lauren, when you say, when you talk about, you know, this fundamental assumption being made of, you know, is it possible to represent language, for example, in n-dimensional space? So is it, I mean, if we were to isolate, not just mapping language, but say, okay, given a sentence, we now imagine regiment this sentence as some series of features, some huge series of features, you know, of that specify its semantics, its pragmatics, everything explicitly in n-dimensional space. If you could theoretically get every feature of potential importance mapped, would you then inevitably be able to get a single n-dimensional space on which you could create a function that would divide it?
So it's really interesting because like it actually like ended up taking like a very different turn, because like, so what you described, right, is that like you're constructing a feature vector for all these like independent characteristics of a sentence, you know? But what the turn that people took, and this was the way this started, was this system called word2vec. And so word2vec was this idea that like by moving a little pivot across a sentence and then looking at the context window for that word, and then if you do it over enough documents, that by understanding a word within its context and the conditional probability of that word given its context, and then vice versa, the conditional probability of the context given that word, that what you get is a spatial model that's not so much capturing these like isolated features. Instead, it's capturing this like deep set of relationships. And I'll tell you something that's really cool. So this is at Google. So after the fact, they discovered that they didn't know that this would happen. But that, so if you have a vector that's like Paris, right? And then you have a vector that's France. France minus Paris plus England, the closest vector is London. It's pretty cool. Like, it's very Wittgenstein. I was at a Jonathan Ray talk and I mentioned this, and he like, I don't think he liked me very much, but it's like super Wittgensteinian.
I think what I was curious is, yeah, do you think that in some ways they may be facing a similar dualism of, well, is the issue that the representations aren't good enough, or is there an intrinsic problem with the idea of sort of a single vector representation of whatever it is that you're trying to classify and identify patterns in?
So I've been working on like kind of what might end up being a paper, and it kind of touches on this actually, which is like basically it's like Okay, so there's stuff that, like, because it could generate realistic language, because it could do, like, it could answer sort of basic questions about a text very effectively, like, it seems like it's fundamentally working, right? So you have this encoding space, right, for sentences. It seems to, like, work fairly well, right? And then the problem, though, is imagine that you have an encoding space for images. So you have two, in linear algebra, it's called a basis or a vector space. So you have two vector spaces. And within them, they have these like well-ordered properties, right? Like that cool vector addition thing. Like, and the image one has that as well because it's an effective encoding. How do you translate between those two encodings? Like, it's something that humans do very effectively. Like, when I read a sentence, when I read about Madeleines and lime tea, I think of like an image of a Madeleine and lime tea. But that alignment, that multimodal alignment between text and images is non-trivial because, like, so do you mind if I go on about this a bit? So, like, if you have like English and Japanese, so if you have one language model that's doing an encoding and it does it for English and Japanese, like, even though they're very different languages or come from different parts of like this linguistic family tree, you could actually learn this, it's called a latent space. So a lower dimensional representation of similarity between these two languages. And it seems to suggest that, like, because languages come from people and there's cognitive structure and semantic structure that generates languages, even though the signifier seems arbitrary, like there's still this like basic similarity even between highly dissimilar languages, which is really cool. And that's why neural machine translation works so well. But like, is that true with images and text? Like, it's a really big open question. There's been limited success, but people are doing really cool work in it. So I think it's like, that's an intrinsic property of human intelligence. So if you want to do anything like modeling something like human intelligence, you have to easily be able to move between images and text and sound and all these different things.
Well, and the symbolic response would be, see, you're just getting to that, like, Platonic language of thought that we told you about. So, geez, you've just taken the long way around to get to what we've been doing.
Yeah, like, I feel like Chomsky probably really liked that neural machine translation thing because that is like support for his generative grammar, right? It's a support that there's like some irreducible thing that's similar across human beings. I think I haven't actually seen publications like about those implications, but it's very interesting.
Actually, I'm going to talk to you about this offline because
okay, cool.
But thank you. So, actually, are there other questions for our esteemed expert here?
Yeah, I have a question. Lauren, thank you so much. I'm wondering if I have two questions. One is just like, well, I'll tell you. So one is that like I'm sort of like thinking about in the context of the multi-layer perceptron, like the role of the bias, and like I don't really understand it, but like it seems like the bias and like the bias has some sort of like sequential role with the way the sort of like bases change over time. Does that make sense? Like,
oh no, I have good news for you. It's far simpler than that.
Yeah, great.
Okay, so like imagine you have like, let's just think of the input layer and like the hidden layer, right? And so imagine that you have two vectors. One is X, which is your feature vector. So it's already gone through this like encoding. And then there's another vector of weights, right? You do a dot product between those two vectors, right?
Mm-hmm.
And so those are like the learned weights, but the bias is this like static thing. So just put one on your feature vector and then put the bias at the end of the weight vector, and then you could still do the dot product. It's just like, so there's this idea in neural networks of this thing called hyperparameters. Well, here, let me give the spatial explanation first. So it like you only open yourself up to like some additional affine transformations if you have a bias, right? So like it's a way of like etching the line in different ways so that you could do things like translation. And then what was I gonna say? Like it's also like it's like a tunable hyperparameter, but it's basically just like imagine you append one to the feature vector and add an additional weight. That's all a bias is.
So it doesn't change over the course of the program as it runs?
No, and so you could, if you look up, I could send this to you, like some of the stuff where it just goes over the math step by step. It's not too bad, and so I think that would like clarify it a lot.
Okay, and then the second question is like, I'm wondering, to what degree like sort of computing speed has to do with the way that people are thinking about sort of like in a larger, more general sense, how I guess like they would say like the state of AI, but that's not to say like sort of computing speed as an efficiency, but like sort of instantaneity, like being able to compute sort of in real time, and sort of learn. Like,
this is highly relevant to my background. So I worked on this. I was at Amazon, and I worked on this, the most ethical company in the United States, and of course, only the best. And I worked on, so this wasn't really neural network based, but some of the stuff we did is stuff that you could also use a neural network for, but it was actually machine learning algorithms that were designed to like learn very quickly, so they're able to like operate on real-time streaming data. So like unfortunately a lot of the people who use this was like the military. I heard that NASA's using the algorithms, so let's think about that. And so like NASA, if they need to like run anomaly detection from this numeric streaming data from a spaceship, like they would be able to do so in this it's called high throughput way. So it would be able to take like a tiny window as a training sample, because it does really fast updates. It'll be able to perform inference in a way where you like kind of barely notice that it's happening. And so this was like the product vision for this series of algorithms was basically like, you know, what if we had machine learning that like, what business use cases would be opened up by having machine learning that like runs this quickly? And then like how would that help? Because like the way a machine learning engineer researcher interacts with a machine learning algorithm is kind of like Rogerian psychoanalysis, because you kind of like ask the algorithm a question and then it gives you back an answer and you just keep doing it, and sort of you're kind of psychoanalyzing the neural network in a way. But like if you could do that much faster, it like makes it more conversational, so there's something more intuitive about it. And it like it's hard to express, but it makes the scientist or engineer more empowered to make meaningful changes. Because one of the things that's interesting and also doesn't get talked about that much is, so I worked with this guy and he has a PhD from Caltech and he's super fancy, and like he just had this like incredibly intuitive understanding of like if there was something wrong with a neural network, like how do you change it? And it's like his mental model of how this thing that is so incredibly alien was functioning has been built up over years, and he's obviously very smart. But like, what if you could have something where it like trains like really fast and you could see results really fast, and like maybe we could all develop those like really rich intuitive models, like and not have to have PhDs or Caltech. So like that's what I would say like the benefits of speed in machine learning are. And if you're interested in this topic, the two things I'd recommend is I'm gonna say three things. Are you ready to write them down? They're like good topics if you're interested in this in ML. So like active learning, which is basically just like when we learn, like when a little kid learns what a cat is, it's not because it sees 5,000 examples of what a cat is. Like it has, you know, the child has curiosity, and so they're able to seek out the most informative like examples of what a cat is and learn very efficiently. And so it's basically doing the same thing for neural networks. So you can see how that would like speed things up. The second thing is there's actually a lot, because this is a very important issue. What's another thing I would tell you to like look into? Oh, transfer learning. Look into transfer learning. Transfer learning is, I think it's like the future. It's very popular in natural language processing, and it works pretty well in CV, but not as well. Is like, so if I have a neural network, let's say I have a convolutional neural network, and I wanted to learn about like very particular rare breeds of fish and be able to classify them, right? It would be really good if that neural network already kind of knew what like an animal was, or like a basic fish was, or like what basic shapes were, so that I didn't have to like painstakingly train it for a long time. And so transfer learning is basically like, what if there's like a teacher network and it teaches the student network, and like then the student network learns faster. So it's a very important area of study, I think.
Could I thank you so much. I just had like one last follow-up question, which is like how would you position or have you heard of, and then how would you position something like graph convolutional neural nets, like this like a geometric deep learning in relation to what you were just referencing?
So that's not something that I know a lot about. But I would say that like so there's a lot of things that could be represented in graphs. One of this very famous important thing in machine learning is called ImageNet, and ImageNet is like basically like 1,000 common objects. And it's a graph in the sense that it's like a tree, a directed acyclic graph, right? And so a lot of times, like, because what a neural network's commonly doing is learning flattened correlations between features. Again, very, very complex ones, but it's all flat. Like, what if you know your data has this graph structure? How do you preserve those relationships and have it like aid your training? So like, instead of having this like very flat data, you have like graph data. And so that's probably like what it is a convolutional neural network over like graph-like data.
That makes sense.
That's an informed guess, so you should check it.
Thank you very much, Lauren. I think what I'd like to do now is take a 5-minute break just for us all to stretch our legs. Lauren, if you want to hear me blab about Frank Rosenblatt and stuff far more primitive than what you've been talking about, feel free to stick around.
No, can I say something? I love this. And the reason why I love this is because like, nobody like you get so like deep into this stuff that you don't ever step outside of it and like think of it from different perspectives. So it's so great. Like, I'm really enjoying this.
Thank you. Well, I'm very happy to have you here. Yeah, you said many of the things that I was hoping you would. So that's great.
Maybe I have a very, very short, I guess it's a very short question, if it's okay before the pause.
Sure. Oh, yeah, sure.
Okay. So
sorry, I didn't, yeah.
Yeah, no, I guess this is pretty absurd, but because you mentioned Wittgenstein a couple of times and that AI is currently confronted with like Kantian questions about, okay, how do we get categories or cognition of causality from pure correlation and pure empirical data? And so it seems to be confronted with pretty fundamental philosophical questions. And I don't know if I wanted to ask if people in AI development read or read also. Maybe not like, it seems that Wittgenstein or something like has, I don't know if they actually read these people, and maybe, but what I'm more interested, if they read people which seem even more absurd, like Derrida, for example. I had to think about Derrida and his paper on Searle and context, as you were talking about, okay, how to, it's not about identifying the meaning of atomized words or phrases or something like that, but okay, interpreting something in a certain context. And I immediately thought about Derrida, and hey, this is not, according to Derrida, this is not even possible to really say, okay, this is context and only this and nothing else. Yeah, because it seems to speak about to a lot of these problems, but no, the deconstructionists don't care about AI at all, as far as I know. But I wanted to know if people in AI development maybe tackle with these kind of authors.
I am the
This is my cat.
Absolute. Oh, I understand that word. Oh wait, I can see. Okay, sorry. So I am like the weirdest person in AI research, so I'm not like a very good example. Do my colleagues read things and make philosophically informed decisions? What I've noticed in AI research is I was privileged to work with this one guy, Pietro Perona, is one of the fathers of computer vision. And like he went from like when he was like a student in like, you know, like Padua, Italy, like he went from like, you know, he literally like invented a differential equation, right? And then as his career progressed, and he's been in this field for a really long time, now he just is like, has become like super Socratic and just like asks like very weird philosophical questions. So I think what happens is like AI researchers start thinking about this stuff like more towards the end of their career as they get like increasingly like opaque and like mysterious and wise. Like that's just something like sociological I've observed. But no, like AI researchers should read way more. I think that that's like a problem, is that people don't really think about the context with which they're doing. And I was talking to a robotics company the other day, and that was actually like the first time where I had talked to like a company that was doing deep learning, where like they were really like interested in a very interdisciplinary perspective. And I actually feel like symbolic AI and robotics people tend to be better. Deep learning people are just like counting their money, you know. Like this symbolic people tend to be like much more open to like a really wide framework. And this is all just like my incredibly biased personal viewpoints.
Okay, thanks. Because I think I'm what is most interesting and also surprising for me is these knots where it seems like, oh, AI research and philosophy seem to converge with one another, and they seem to be non-distinguishable at times, or at least tackle the same questions. And I think this is that's because what I'm interested in that.
Well, so one of the things I'm interested in, I just like have always been very fascinated by Wittgenstein, and I was just reading something interesting about how he was very resistant to historicizing his work. He was very resistant to reading the history of philosophy, and he saw philosophy almost as a psychoanalytic project. And it was about this untying of knots, like you said, is that you find this concept and you just sort of like, you know, tweak it, and it's like profoundly subjective and kind of ahistorical. Like in his view, it's almost like monastic, right? Like a care of the self kind of thing. And I think it's interesting, like, because what happens if you take Derrida? What if you take difference and you look at it in the context of encodings, or you take Wittgenstein, and encodings are very explicitly tied to Wittgenstein. You're taking this profoundly, like you're taking their ideas, but it's like you're taking their ideas outside of their philosophical practice. And I think that could be dangerous, almost like I think Wittgenstein would hate the fact that word to vec is so like commensurate with his ideas, because it's like, I don't know. I think it's an interesting question. Like, what happens when there's these knots where these two disciplines meet? Is there something that's lost, you know, like in scientists being inspired by a writer or a philosopher? Like, do you miss something? But yeah, sorry, this is an interesting question.
Oh, thank you very much. Thank you.
There's a book called Wittgenstein's Remarks on the Foundations of AI, which I have not read a lot of this yet, but which may be of interest to some of you. It actually, I guess it dates from 1998. It's by Stuart Shanker, but it has him talking about Turing and Gödel. His remarks on Gödel are just bizarre. Anyway, actually, so let's take a couple minutes. Feel free to keep talking. I just need to go and refill my water, but feel free to keep going. And we'll start up again formally in 5 minutes or so. Here's a cute recreation of Eliza. Okay, is everyone back here? I'm going to get started just because I really do want to get ahead. For what it's worth, I think I said this last time, but we do not have class next week. We do have class the week after. I'll find no class. All right. So yeah, we're going back in time a bit. The perceptron is in many ways the prototype of the sorts of systems that Lauren was speaking about. That you feed it that effectively it's trying to create a linear function that divides a plane between right answers and wrong answers, so that to any sort of problem, and if you tweak the function by adjusting its constituent nodes, the perceptron will hopefully get things right a greater percentage of the time. And through this training process, you can say the perceptron learns in a formal sense. The weights get within the nodes get adjusted. And that becomes the root of machine learning and neural networks. And the work since then is how to make it so that the classification can be both more complex and more accurate, which is no easy feat. Rosenblatt is drawing from the same insights as McCulloch and Pitts by observing again that the nervous system consists of these individual neuron units that have thresholds of activation and work in parallel, and he wants to put them to use by seeing if they can be conditioned to achieve particular practical ends. This is on page 573 of the Rosenblatt reading. It is an attempt to study the psychological properties of certain highly simplified mathematical or physical models of the central nervous system in the hope that such a study may throw light on basic principles which can then be applied to more sophisticated models. Rosenblatt's genius, I think, is to reapply McCulloch and Pitts's insights in a different and more practical direction. Instead of creating a logical equivalency for a nervous system, he hones in on the possibility for the conditioning of a somewhat simpler neural network in a way that can actually be implemented. And I'm just going to put this picture up. Let's see if I can do this. Share. Is that showing up right now?
Yep.
Yeah, okay. So it's a basic topological structure of the nervous system and its sources of information. He says, okay, this is on in the preface, page 6. For this writer, the perceptron program is not primarily concerned with the invention of devices for artificial intelligence, but rather with investigating the physical structures and neurodynamic principles which underlie natural intelligence. A perceptron is first and foremost a brain model, not an invention for pattern recognition. As a brain model, its utility is in enabling us to determine the physical conditions for the emergence of various psychological properties. It is by no means a complete model, and we are fully aware of the simplifications which have been made from biological systems, but it is at least an analyzable model. Okay. So what comes out of this is something that is entirely mathematical, and that's why it's called subsymbolic, because at the end of the day, the perceptron doesn't know much about anything that's being done to it, no more than a neuron in the brain knows about what thoughts might be occurring. And yet there it goes, it's actually behaving with something approximating intelligence. And this, it is a threat to the symbolic AI way of doing things because it doesn't meet the necessary conditions Simon and Newell put forth of needing a physical symbol system in order to behave intelligently. Now, there's a dodge because you can say that, well, the physical symbol system is there emergently, but neither side is happy with that dodge. he does make an overture to Rosenblatt makes an overture to symbolic AI on page 52 when he suggests that perceptrons could be built up into a symbolic AI kind of structure, because that's one of the nice things about subsymbolic, which is AI, which is that it's at a lower layer of abstraction, and so at least theoretically it could be built up into anything, just like the brain. Of course, symbolic AI wants to cut to the chase, and just because perceptrons are so general purpose doesn't mean they perform well on all tasks. And I think Lauren was speaking to that earlier. One of the sayings in the 90s was, neural networks are the second best way to do anything in AI. And that's certainly how the symbolic AI people thought of it, although they said, it can't even do anything, you just do a lot of things. Why bother conditioning all these networks when you can just code the logic explicitly, is the symbolic response, is the symbolist response. So again, perceptron, it's something that deprioritizes the logic of symbolic AI and emphasizes, in particular, this topological network. And you can see here that, okay, here is the nervous system envisioned as a topological graph of units functioning in parallel. And Rosenblatt also, in tandem with this, Rosenblatt wants to reintroduce sensory modalities quite strongly, moving away from the abstracted notion of thinking, which the the symbolic AI people are concerned with. And this is on page 38, where he says, a typical cell in the cerebral cortex receives input connections from some hundreds of other cells, which may be located in widely scattered regions, but its output is more likely to be transmitted into a relatively localized region. Experiments by Sperry and more recently by Letvin show that if the optic nerve is severed and allowed to grow together again, the fibers which originally transmitted to a particular terminal location will tend to reconnect to that same terminal location with surprisingly little loss of precision. This points to a highly specific neural organizing capability, which must be taken into account in considering admissible types of constraints for a brain model. In the mammalian brain, each sensory modality appears to be represented by an orderly mapping analogous to that just described. Possibly an overstatement. But this passage is clearly a huge emphasis from cyberneticians here. I mean, the return to the analog, return to concept of an organism in the environment, all of that. But Rosenblatt, because he's got computers, there's some real advancement. These are covered well in the Nilsson excerpt for today. If you want like a simple description of linear classification performed by a perceptron, the Nilsson's excerpt for the connectionism reading is a pretty good one. And I'm going to stop sharing right now. Back to me. But the thing to remember is these are most definitely not problems of formal logic, but of mathematical classification and pattern recognition performed through fitting and statistical means. So in contrast to the ready-made mind that the symbolic AI people are proposing, Rosenblatt stresses this training process with emphasis on learning, memory, and temporality. In the place of Simon and Newell's use of Gestalt psychology to gesture to some emergent thought, Rosenblatt involves Gestalt psychology with regard to sensory apperception. There's a difference. That's not day and night. Simon and Newell's Gestalt related to their sense that no matter how the brain was organized, there had to be some emergent logical level, symbolic and logical level. Rosenblatt's Gestalt relates to his claim that no matter how the brain is organized, it must be able to group raw sense data into patterns and apply criteria to those patterns. But Rosenblatt affects a return to functionalism by saying that each operation performed must be clearly assessed as either being a success or a failure, simply so that the perceptron can be tuned so that it classifies things correctly. Symbolic AI doesn't have that quite sense. A symbol manipulation is true in its very essence, and there's no process of error connection innate to the system unless one considers the coping mechanisms of heuristics to be a kind of error correction, which I would not say that they are. And Rosenblatt wants to stress that the perceptrons can be trained to approximate the functions being explicitly coded by the symbolists. So he says that, in fact, we can get to the symbolic AI level fairly quickly from the perceptrons. And, as Lauren was pointing out, that's an overstatement in itself. Now, Rosenblatt admits it will be less efficient because whatever function the symbolic AI people code, it has to be mapped into this pattern recognition learning language. But Rosenblatt insists we can get there, and he also says that this is how the human brain itself works, which seems to be not an unreasonable contention. So it's a clever move he makes to unite symbolic and sub-symbolic AI by saying that sub-symbolic AI can subsume symbolic AI. And at the end of the book, he makes these claims. He says, look, this is on page 584, the most important technological development which may be inherent to the future development of brain models will be the provision of eyes and ears for conventional computers and automata, giving them a common universe of discourse with their operators. Current attempts at heuristic problem-solving programs, such as Newell and Simon's programs, and at automatic language translation are hampered by a lack of common reference for symbols, which can be no more than code numbers for the computer, but which have a wealth of associated meanings for the operator. The development of a system which, by virtue of shared sensory experience, can comprehend the nature of the physical reference in a descriptive statement is probably a necessary first step to the creation of a truly useful problem-solving computer. Linguistic capability related to perceptual experience is of the essence for an intelligent system, artificial or otherwise. As advanced perceptron models become more sophisticated in their psychological properties, it becomes more appropriate to consider them as devices capable of performing arbitrary programs of observation, response, and manipulation of data. All right. So Rosenblatt desires this bottom-up model by which the cybernetician's dream may come true. He points at the symbolic AI gap that Weizenbaum and McDermott will discuss, and he seems to hint that it's embodiment and sensory apperception, pragmatic specificity in the world, in other words, that lends actual weight to the symbols being manipulated abstractly by physical symbol systems. But this does return to von Neumann's concern, which is that these sub-symbolic equivalences may be incredibly inefficient. And that's what opens up this line of attack that Minsky and Papert take in their book Perceptrons. Just the name itself is ironic because Minsky in particular had done some work in sub-symbolic AI in the 50s, but had utterly left it behind by this point. And this is in 1969, I think. And so his engagement with perceptrons has been read as being politically motivated. And when in the first section they title a subsection Seductive Aspects of Perceptrons, you can see where it's going. Minsky and Papert contend that the sort of learning done by perceptrons doesn't generalize. On page 16, they say, but we believe that significant learning at a significant rate presupposes some significant prior structure. In other words, they want to say that symbolic AI is prior to perceptron-based learning. There must be some sort of semantic infrastructure. In other words, the semantic gestalt is prior to the classification and pattern recognition gestalt. There's irony here, since the lack of generalization was exactly the accusation already being thrown at symbolic AI. The irony was that the problem facing perceptrons was in many ways similar to that of symbolic AI, just more so. Just as the symbolic AI people were asking for more time, so was Rosenblatt. When he talked about multi-level perceptrons, the processing power simply didn't exist to get there. And so Minsky and Papert were able to attack the set of perceptrons that could be implemented at the time and appeared to somewhat elide the fact that there was a degree of unexplored possibility beyond that, which simply wasn't computationally instantiable in the 60s. So the question is this a practical argument or a theoretical argument, or has been, as has been the case very often, something somewhere in between? The book had certainly had some impact on subsymbolic AI research. The Olazar makes a case that subsymbolic AI research never truly died off, which is true, but it didn't really take off until the next generation of researchers, like Rumelhart and Hinton, and some of the other folks that Lauren mentioned, came to prominence some years after the Lighthill report, around 1980 maybe. Rosenblatt's early death might have been a major cause too. And the way Terry Winograd speaks about it in 1989 is that he thinks it's mostly a matter of expediency. Because I think there's a tendency to, this is from Speaking Minds again, I think there's a tendency to abandon hope for quick riches. It has been obvious from the beginning when they tried to build machines that learn, Rosenblatt for instance, that it was going to be a very slow and difficult process. On the other hand, when you came in from the symbolic end, that was the first thing you got to. For example, geometric theorem proving, which was presented as early as 1956. So it appeared that the higher level phenomena of language and formal thought would be very immediately accessible for the symbolic mathematics and only extremely distantly available for the so-called lower level computation. The decision in the research centers was to try to go for it quickly. And, you know, one can, extending that line of thinking, one can now see that perhaps it has flipped around, that symbolic AI came to look too difficult and the quick riches moved into the sub-symbolic area once the processing caught up with them. But there's still a philosophical debate going on under the sociological conflict, and it centers less on functionalism, as it did with symbolic AI's response to cybernetics, and more on a focus on epistemological primacy. I earlier referred to Rosenblatt as taking a more pragmatic approach in contrast with symbolic AI's emphasis on semantics, but I want to develop and complicate that a bit further. On page 234 of Perceptrons, Minsky and Papert effectively reverse Rosenblatt's contention by saying that symbolic AI, the physical symbol system, must be prior to any sort of pattern recognition. Is on 234. All these processes might be organized by a supervisory program like the GPS of Newell, Shaw, and Simon, or the executive program of a large programming system. A system with such a set of abilities is in a very different class from perceptron, if only because of the variety of operations it performs and forms of knowledge it uses. People often suggest that the methods of AI and those associated with the perceptron are not as opposed as we think. For example, they say a perceptron-like algorithm might be used at each level to make the separate kinds of distinction. But using a perceptron as a component of a highly structured system entirely degrades its pretension to be a self-organizing system. If one is going to design such a system, one might as well be pragmatic in choosing an appropriate algorithm at each stage. In other words, the algorithm is primary. Minsky here, I think, is as clear as he ever was in saying that neurons and perceptrons serve the algorithm rather than the other way around. And in turn, the implication is that even in the natural world, a pseudo-Platonic realm of algorithms and logical operators exists that is instantiated by our brains. We now may not know where these algorithms, what they consist, but like the process of anamnesis, they are out there to be discovered because they have to be. It's a naturalized Platonism. And John McCarthy, in his characteristically blunt way, says this more explicitly in a quote that Bowden cites on page 869. This is from 1974 in his response to the Lighthill report. He says, if we take Lighthill's categorization seriously, then most AI researchers lose intellectual contact with Lighthill immediately because its three categories have no place for what is or should be our main scientific activity: studying the structure of information and the structure of problem-solving processes independently of applications and independently of its realization in animals or humans. Again, that last part. Studying the structure of information and the structure of problem-solving processes independently of applications and independently of its realization in animals or humans. Okay, this is a wonderful quote because of how much is packed into this single sentence, both in terms of philosophical outlook and in terms of philosophical assumptions. Leaving aside the structure of information, which draws from Shannon, and which is a problem that is not only broad enough for all AI, but for many other fields as well. McCarthy hypostatizes the existence of generic problem-solving processes which can be instantiated in algorithms. And via Minsky, we place such processes prior to their instantiation by a particular brain organization. This is a close relation to the physical symbol systems hypothesis, but it's clearer about what the symbolic AI people were up to when they were trying to define thinking in terms of the physical symbol systems hypothesis. Simon and Newell said that a physical symbol system was necessary and sufficient for general intelligent action. And here we have what general intelligent action consists of: structured problem solving. So somehow we have returned to the original question we posed at the very beginning of this class, which is, what is thinking? And the symbolic AI people had, perhaps half unintentionally, entered into a discursive space in which thinking had to have a far more definitive outline than it did for the cyberneticians, who could marginalize it as some consequence of homeostasis or adaptation. The symbolic AI people imagine a teleological or perhaps metateleological substrate to the world in which all purposive action can be abstracted away from all particulars and framed in a language of logic and algorithms, a Platonic language from which both thought and human language can be derived. So while the symbolic AI people are concerned with semantics, we can go further and say that any semantics which they thought to capture had to fulfill this greater criteria of generalized problem solving. That is, a semantics is more than just a matter of denotation, but also a matter of goal creation and problem solving, heuristics being a large part of that. But just as Hubert Dreyfus had used Heidegger to elevate background knowledge to an ontological level that he claimed AI could never capture, the symbolists used Carnap and logical positivism in the service of elevating problem solving to an ontological level that AI could capture rather easily, at least at the conceptual level. And what I want to say is that both sides of the debate are pulling that ontological. Weizenbaum doesn't, because he's more of a Pyrrhonist, and Lighthill is cagey about it. But what you have in McCarthy, Newell, and Simon is really an ontological claim that very much in the order of Heidegger, and thus an ontological argument occurring in the guise of an epistemological argument. The gestalt to which Simon and Newell allude is not a psychological gestalt, but an ontological one. And this ontological gestalt of logical symbolic problem solving is that which must be captured before any thinking can possibly occur. There's your necessary condition. And there's a parallel to mathematical Platonism here. The conventional wisdom is that most mathematicians are offhand Platonists because it's difficult, or weekend Platonists, because it's difficult to do math and not come to think that there are mathematical truths out there in the world waiting to be discovered. Somehow the symbolic AI group came to believe the same problem solving, that there are problem solving algorithms out there in the world to be discovered, independent of culture, independent of species, and that to consider any problem, is to find that at a sufficient layer of abstraction, you can universalize it. And not that Rosenblatt or perceptrons are immune from claims of universalization, but Rosenblatt goes about it in something in a different way. Instead of universalizing the ideas of problems and solutions, he universalizes the ideas of learning and error. That given any specified task, and by task I mean something less than a problem, not of figuring something out and explaining one's answer and reasoning, but simply of giving the right answer, whether you know why you did it or not. Given such a task of that sort, Rosenblatt believes that his mathematical model can universally learn by making mistakes and by being tuned and trained to give the right answer more of the time. It's not an epistemic universalism because it doesn't elevate problem solving to an ontological status. Rather, it's a methodological universalism because it claims that any task, however it may contribute to some pragmatically defined problem, can be tamed through a universal method of mathematical conditioning of nodes in a perceptron network. And he says that this is how the brain must work as well. Metaphysics does not instantiate teleology, but it does instantiate learning behavior. And as Nilsson says on page 105, any technique for pattern recognition, even those using neural networks or nearest neighbors, can be thought of as constructing separating boundaries in a multidimensional space of features. And to the extent that you can define any problem as pattern recognition in a mathematical or topological sense, and many problems can be represented as such, and Rosenblatt certainly said that, then you can say that pattern recognition is ontologically primary. You don't need to worry about the structure of problem-solving processes as much as McCarthy said, because from Rosenblatt's perspective, you have hit on the structure. No greater structure is needed. So instead of the physical symbol systems hypothesis, you might call this the mathematical pattern recognition hypothesis. That mathematical pattern recognition is what is necessary and sufficient for intelligent action. It's its own sort of leap. Instead of epistemological primacy, you have primacy, a method that gets you to many things, some of which are thinking. And this is a parallel from the movement from Kant to Peirce, from the focus on conditions for knowledge and thinking to the focus on conditions for learning and acquisition, category acquisition among others. But it does bring up, I think, and Lauren and I did not coordinate before today, the questions that Lauren was raising regarding whether these sorts of vector models, these sort of topological spaces, can actually capture the full gamut of logical thinking. And from there, I think we move. That's sort of what I wanted to say briefly about the perceptron controversy, because even though perceptron research definitely took a backseat for a while, by the late 70s and early 80s, there was a new form of research called that termed itself at the time parallel distributed processing, also termed connectionism, that really did aggressively expand on Rosenblatt's basic ideas of some subsymbolic AI. And to that end, I would like to now turn it over to sorry, who is doing the Rumelhart paper? Brian?
Yeah.
Awesome. Brian, why don't you take it away? And I think we have enough time.
All right. I'm going to try to just share the screen for the paper. This one here. Let's see if that works. And then Are you guys seeing the, what are you seeing right now?
Yeah.
The paper?
Yeah.
You're seeing the paper? Okay. All right, I'm just gonna have that up just so I can point to some of the diagrams that.
Oh, and just before you start, that is Jeffrey Hinton as the co-author, one of the godfathers of all of this stuff. So, anyway, sorry. Go ahead.
Yeah. Okay. So, a lot of this paper seems to be responding to, problems and obviously issues with efficiency and with limitations to symbolic AI and to what they talk about as the dominant theme of using schemata, frames, and scripts as knowledge structures, and the idea that those types of that you could encode knowledge into sort of hierarchical scripts, then that forms the basis of comprehensions. But then you get different types of issues, one with like efficiency and speed, and then also with they ask, how can generative understanding occur if you've got those kinds of formal scripts for producing a response. So one thing I said, I think that the idea of a script, as I'm just going to kind of say the things that I said as I was working through these ideas. So the idea of a script is you maybe have a single source of knowledge that constrains or orders actions or orders recognition. Also, it seems like parallel distributed processing models are either dealing with recognition or producing an action. So recognizing a word or producing a movement, like they talk about, like, for typing is the first example they use. Parallel distributed processing tries to account for, basically is this theory, models that try to account for human knowledge using scripts. Like knowledge structures will have to allow them to interact with each other. So this idea that if you want to have generative, if you want to give a system a generative capacity, like human understanding in novel situations, that you'll have to have those scripts that encode knowledge able to interact with each other. So they propose this idea of understanding through the interplay of multiple sources of knowledge or mutual constraints that each constrain what something's going to be recognized as, or the action that's going to be produced. One thing I thought was interesting about this, beginning like that juxtaposition of thinking generatively versus constraint, and they talk about how human thinking, when we add more constraints, it actually makes us faster. But if you're using a purely like a linear or sequential script system, it takes longer with more constraints as you add them on, because it has to do more iterations. So they're trying to make this more, these models work better, or to achieve the same increase in efficiency, which is through more constraints, actually making it take less iterations to recognize something or to produce the correct action. So let me see, hold on here. So then you got reaching and grasping, multiple simultaneous constraints. So parallel distributed processing is a class of models where all pieces of information simultaneously influence each other. So information processing takes place through large numbers of simple processing elements called units that can each send excitatory or inhibitory signals to each other. So units, they stand for hypotheses, so possible hypotheses. So they talk about a few different things how you can interpret what units are, but I like the idea of a hypothesis, and I think that it maybe underlies even the other different ideas of what the units are. But the possible hypotheses, for instance, like which letter something is, recognizing a letter in the context of a word, or you might have a higher order of a unit that is to recognize the syntactic role of a word within the context of a sentence. And then you also might have units that stand for, and these are like the nodes, and maybe what would be eventually a neural network, Then you also have units that might stand for possible goals and actions, or sub-goals and sub-actions. So on the one hand, you've got, in terms of recognition, you could have two levels of units, one for recognizing letters, and then a level of units that recognizing the letters within the context of a word, and then you have recognizing the word, the syntactic role of the word in the context of a sentence, and then that is sort of paralleling a different use for PDP models, which would be possible goals and actions, and then within that you'd have sub-goals or sub-actions. So this here is an interesting kind of paradox that they propose, which is that we're able to figure out what each letter is, even though without the context of the other letters, it would be maybe impossible to figure out what they are. And they resolve that by saying that each of these things kind of each letter mutually and simultaneously constrains our options for what each individual letter is. It's not that we, have to, perform these sequential iterations of figuring out what the R is, but actually we're able to have them all constrain each other. And when you do that, it becomes the total number of options that this letter here could be becomes very limited to maybe R. Okay, so they say that cognition itself does have a sequential character to it. Ideas come and seem promising, and then are rejected. This leads to a solution to a problem. A solution to a problem are taken up, then abandoned and replaced with new ideas. But if implemented sequentially, each macro step of cognition requires vast numbers of microsteps. This poses problems for time limitations. The process would be sluggish. Additional constraints make it slower, but of course, human thoughts get faster with more constraints. So PDP mechanisms are used to provide natural accounts of the exploitation of multiple simultaneous and often mutual constraints. So instead of sequential iterations, PDP employs multiple simultaneous constraints and can make cognition faster. So they talk about here the performing an action, the keystrokes for vary. Each letter of the word is a unit. So you have each letter here is a unit, and then you've got a unit for the word itself. And this later on in this paper starts to confuse me / it's interesting because, and if you've got some insight into this as I go along to help clarify, because I've just got a couple of different competing understandings, competing nodes in my mind as to whether this in particular whether this would be considered a local representation or a distributed representation, because it seems like since you've got a pattern here, you've got multiple nodes that could represent a word. I guess I'm conflating this with the things that are happening later on in some of the more complex versions that they talk about, and trying to interpret this one. But it seems like this might be a local representation, but later on we're going to talk about how distributed representation. But anyhow, each letter of the word is a unit, and the word is a larger scale unit. So each letter constrains and inhibits the activations of the letters. And then you've got these competing constraints with reaching for an object without falling over. So you've got two different goals. You've got kind of a sub goal. You got reaching for an object, but when you do that, it moves the center of gravity, which would make it fall over. So you have these competing constraints. You have this, on the one hand, you have the need to move arm forward, that's the object. The other constraint is need to maintain center of gravity while moving forward. And both of those constraints together lead to the sort of behavior of the PDP model. So at first, each processor attempted to achieve a solution. They had 6 processors each. At first, when they were trying to achieve this, they had 6 processors each at a different joint. And since each processor was trying its own iterations at different times, and I think this is all hypothetical, right? This is nothing they're obviously doing at this time. Is that true, David?
I mean, they're being simulated, but certainly it's not being done.
Right. So they're
No.
Right, they're simulating it, right, not robotically. And even later on, they're simulating like memory retrieval. And I'm not sure if they have the actual computational abilities to even do the basic memory retrieval at that point that they were doing. But anyhow, they were doing, each of the 6 joins was doing different iterations. So it was taking too long. So instead they took, instead of having 6 processors, they had 2 processors and 1 which took the mutual constraints for basically the 3 joints that were involved in moving the arm. And then they had another processor which involved the constraints for moving the body to move the center of gravity. So then they start talking about perception and familiarity down here, and our ability to complete familiar patterns. So this is something that most of us understand, like if you were to hear the word legislature and with a click instead of an S, we still experience it as if there was an S in there, and the click seems to be just some sort of disembodied sound that we're hearing. And they're basically saying that PDP could account for that kind of perception. So they propose a model describing the role of familiarity in perceptions based on excitatory and inhibitory interactions among units, standing for various hypotheses about the inputs at different levels of abstraction. And then you have competitive inhibition. So you've got mutual exclusion and between level inconsistency operating in the word perception model to reduce the activations of units. Thus, the letter units in each position compete with all other letter units in the same position, and the word units compete with each other with all other word units on that level of abstraction. So then you have inhibitory interactions between incompatible units on different levels. So at each level of abstraction, you've got units that, when they are activated, are also inhibiting the other units. So I think that competitive inhibition happening on multiple levels of abstraction seems to be important for this. So their models, they claim, have the ability to complete novel patterns. So they are basically able to have the hypothesis of the one whole PDP model might be itself kind of like a hypothesis for the whole orthographic structure of English. So the orthographic structure could be a unit or a hypothesis. So basically they're saying that their models would be able to be able to, like, they give the example of adding, past tense to words that, couldn't have past tense, or adding past tense to irregular words. So instead of, to say like this person came here, came over, you could say that the model might accidentally produce things like this person camed, C-A-M-E-D, and add on, confuse that. And they're saying that this is actually that's actually in the right direction, because that's similar to how young children make mistakes, and it's indicative that this type of model is actually learning basically rules without actually having to code in rules, that it's learning rules and able to act on in novel situations with what appear to be rule-based behavior when it's not actually rule-based behavior. So these models have content addressability. So just like human memory is content addressable, we can access a memory based on any part of its content, but the more unique the content is to that memory, the more it's going to specifically call up that memory. But since unique content is rare, usually we remember through a mutual interaction or simultaneous constraint of multiple pieces of general content that together are unique to that memory. So the memory then, I think in this case it's interesting, because I think in this it's interesting, like as far as what is being stored. And later on they go on to say that memory isn't there's no like piece of hardware for each memory. You don't have a node or a unit for each memory, but rather you are storing connection strengths between nodes.
And this has, I'm so sorry to interrupt, but like this is like incredible. Like, so Hinton has this tendency to like really absurdly understate his findings, because he's an incredibly like humble person that's constantly challenging his own ideas. But basically, like, instead of like, imagine that you have a database and you have to like store all of human knowledge in it, right? Like that database is going to scale linearly with the amount of human knowledge. So it's going to be like infinite basically. But like once you have a distributed representation and you're just learning relationships between items, as long as you have a sufficiently expressive model, like you have finite memory that doesn't vary with the amount of information. So like you could be exposed to an infinite amount of information. And as long as the model's sufficiently complex to like map those, like, you know, capture those like local representations and relationships between all the data, then like you have like finite storage of knowledge of that information without having to store that infinite information, you know, probably like the human brain. So it's like a very profound consequence of this.
Yeah, because you don't have to search every piece of knowledge in some kind of database. And they also say that it works better than indexing, which is basically a more organized use of a database. But thank you, that I can have said it that well.
Yeah, and this is, just to add, you know, this is one of a way of answering von Neumann's and as well as Minsky and Pappert's critique of, oh, aren't the representations going to be so huge? Well, maybe this is, the question is, okay, well, how could the brain possibly do it? And they're saying, well, maybe we figured out how.
Yeah. Because, okay, so moving on, it talks about graceful degradation, which is basically like errors are not going to lead to not necessarily, so if you get you know, imperfect information, it's not going to necessarily make it so that you're not going to pull up the right memory, because at least if enough of those things, if enough of the cues that you're getting to call up a memory are more associated with that memory than they are with a different memory, the error is not going to lead to filtering it out. But if you were to say, let's have, you know, a stored database with like a stored database with explicit information with a particular address, you're going to need an actual address, and misleading information could filter out or lead you to never get to that address. Whereas with this, as long as you're basically lighting up enough of the nodes that are at least unique enough to that particular pattern, then you're going to end up with the right memory, which seems to be more similar to the way that humans do that. And also within that same, as a result of that same process, you get default assignment, which is the tendency for this model to fill in extra information by exciting groups of units that are similar in most regards, and lighting up a node of similarity that may not be known. For instance, they're talking about Lance. So basically they're saying like, if you're recalling, or if you're accessing information about, you know, one person, and that person tends to be, if Lance is just like you know, Ralph and Fred and Pete in every other way, and we know that Ralph and Fred and Pete are, you know, burglars, then a natural consequence of this model will be to also fill in and to kind of make these like role assignments that at least until further information, some kind of strength or hypothesis about that also Lance is a burglar, because until that's different. So they'll talk about that again later. So also patterns in PDP are not stored, just connection strengths between units. That's really essential to all of this, that you're just storing connection strengths. And that's I'm just trying to get to the local versus distributed representation part, because I think that that's really interesting. This part here, as far as this kind of, they talk about is this orthogonal, and this is a belief in how a pattern associator works. And this is talking about kind of how if you were to get the smell of a rose, that you could also recall the visual sensations of the rose. And they say that this can be pulled off through having this sort of orthogonal PDP model here. I started to understand that, but it's a little bit blurry to me now. So maybe we can return to that later if somebody has a real clear way of explaining that. Okay, so I'm going to move forward to talking about chapter 2 because it kind of returns back to and clarifies some of the other things going on in chapter 1. Okay, so distributed representations. At first, I think with PDP models still also they were used, it seemed like local representation seemed to be the most straightforward way of employing that those kinds of frameworks. They're easy to implement, and that's kind of where you have a piece of hardware or processing unit for every piece of information. And they propose, instead of having kind of a unit that is associated with every kind of queue or every possible piece of information, each entity is instead represented by a pattern of activity distributed over many computing elements. Each computing element is involved in representing many different entities. So that's that's the main part of, that's the kind of main point they're going to keep coming back here about this model, is that you can have the same set of nodes, and it's not that each node represents some specific, feature about another set of nodes or about the, the real world, about whatever, knowledge source, but that set of nodes, a pattern of connection strengths between that set of nodes refers to something else, as opposed to having each one of them refer to one-to-one correlation between like a node and a thing. You have a pattern. So then you can have this, let's say 15 nodes code for whatever, I don't know how to do the math on that, but millions and millions of different either inferences or pieces of, they've got micro inferences and they've got micro features. And you could have a pattern be a micro inference or a micro feature, instead of having to have each unit or each node be referred to a feature. So that makes processing abilities simpler. It makes it harder to store arbitrary information when you do it that way. They also make it a point to say that it's not an alternative to a semantic network, but a way of implementing a semantic network, but that has some emergent properties. Those emergent properties are things like we talked about: content addressability. So any piece of information can be used to draw up a memory, even if it's not full, every part of it, even if it's imperfect. You get that automatic generalization where you can fill in extra, you can use rules that haven't been applied to novel situations and apply those rules to novel situations. And they can be tuned to a changing environment. So, and the basic idea is that each item, like an item in like that's being referenced to or referenced or as part of your knowledge source or a queue, each item refers to or is represented by different patterns of activity over the same hardware units. Due to this, it's impossible to point to a specific place where memory for a particular item is stored. And I'm sure that's a conceptual hurdle that, through this time everybody was kind of maybe going through, is that you don't have a particular place where a memory is stored. They're rather stored in the connection strengths, which are at the same time, those same connection strengths are also coding for other memories. So then when they go in and try to tweak to add in to code for a new memory, and you try to tweak the connection strengths, you can throw off, if you do them too quickly, you can throw off other other patterns or other stable patterns. So each active unit can represent a microfeature of an item, where the connection strengths stand for the micro inferences between microfeatures. And then they keep talking about this idea about a stable pattern of activity, but I don't really see him going into explaining like what that is. But it seems like instead of needing to have like a unit for every particular item, you can have a stable pattern activity. Whereas you have after enough iterations or enough like training that you get a stable pattern out of that. And I think it might be interesting to continue to explore the relationship between stable patterns and items. It looks like are we out of time? I'm not done with this, but
we're
yeah. I mean, let's Yeah, why don't we're going to be talking about this next time anyway. So if you want to pick up and finish saying what you'd like to say, this has been really great. So it's probably worth doing a brief like recap of it anyway. So yeah, the interest is, as far as stable patterns, that can also be seen as a form of the cybernetician's homeostasis. There's a link back there, but I hope you can see that yeah, that what this is this is quite a development of the work of McCulloch and Pitts first, and then Rosenblatt, and yet one that's been hybridized with at least the language of the symbolists. And on that note, again, no class next week. For the following week, it would be nice, since we've got 2 weeks, why don't you try to read all of the deep learning readings as well, and then we will see how far we can get both on connectionism and deep learning in 2 weeks. Any email me any last questions? Okay, thanks again to Lauren for chipping in. Thanks to Brian and William, and I will. Oh yes, Brian.
Sorry, I did want to just because it's related to something that Lauren had said earlier about because I had this question. We don't have to answer this, but I just wanted to at least just say it, just to pose it. But I had this question about when they're just trying to take out, you know, all of the actual like units that represent particular items and always have it be a pattern. But if you a pattern of activation. But at some point, if you just got these layers of abstraction and like, you know, this pattern down here activates this pattern up here. So that's how we know that it is, you know, referring to Lance, but Lance is really just a pattern, right? But then if you have, you know, but that pattern then, in order to refer to it as Lance, has to go up to another level of abstraction. At some point, do you get to a point where it's actual hierarchical and you have a particular unit for, because it seems like that's how deep learning is, where it has to create a functional response. But if it's just patterns of activation all the way up, how do you get eventually some kind of expressible functional response that's totally particular and not a pattern of recognition? And I also thought that this was kind of related to that question of like the idea of like having an English correlate word for a French word, where at some point you make that transition and say, oh, this is this English word. You know, first it's contextualized, right. Okay, how we know that this is this English word, well, but how do you communicate, or how do you create a functional response without having like this ultimate reference point that says this is the thing that it is that I can communicate to somebody?
Right. Well,
oh, go ahead, David.
The cybernetic answer, I think, is you know, we can look at it as Ashby's answer, that it's still just a model of selection. If you've got a way to make the right selection, you've got your answer, and everything else is a black box. Now, you know, that's a bit of a Hail Mary pass or a dodge, but that's at least, you know, the, okay, well, we don't need to necessarily confront that question head on because we can at least appeal to that possibility.
So the deep learning repost is like, so this is actually like really easy to think of in terms of images. I think it gets like extremely opaque when you think about it in terms of natural language, and the model topologies for natural language tend to be like fairly complicated because you have to have these like long-term, short-term memory like components, because like language isn't like strictly sequential in meaning. Like a word very far down in a sentence could like reference a word very early on. And so you have to like model what they're called recurrence relationships, like sequence relationships. So sorry, that was a long caveat, but like when you think of it in terms of an image, it's actually very easy to understand. So like imagine like we were looking at like images of dogs versus images of wolves, right? And so all we want to do is we want to like, let's say we have a 3 because it's RGB channels and then 25 by 25 size images. So we want to take those images as input. And then finally at the end of the network, we just want to output like, you know, a vector that's either like 1 or 0, you know, like, is it a dog? Is it a wolf? It's just a binary classification task, right? So fundamentally, right, like there's a change in dimensionality because we're going from those 25 by 25 by 3 images to like some sort of one hot encoded class vector that's either like 1 or 0, dog or wolf. And so the way that it's done, and to incorporate your very good explanation of local and distributed representation, is that the first layers, I'm not going to go into what makes a convolutional neural network, but I'm happy to follow up. But like the first few layers are just understanding extremely simple features like, oh, this edge indicates that there's an object, right? And so what they're doing, right, is imagine like a little window that's moving across the image. That window is learning like the things that are most important in the image to pay attention to. And so what you keep getting is this downsampled version of the image, like as those convolutions, and then it's called pooling layers, are applied over and over again. And so at some point in the convolutional neural network, you have this local representation of like, let's say like a doghouse and a tree and snow or something. And so those are like more high level features. So obviously we have to go like a few layers in until we get those local representations. And so like at some point, right, like it almost becomes symbolic AI, because at some point it's like, if it has a doghouse, and it's very likely, the probability is high that it's a dog. Or if it has snow, the probability is high that it's a wolf, right? And so you can actually extract layers of the neural network that do have these local representations or something that would be semantically meaningful to a human. And when you look at like visualizations of neural networks, like there's visualizations of like Deep Dream and stuff, it's actually pulling out those intermediate representations. And so finally, it's like what always is at the end of these convolutional neural networks is what's called the densely connected layer. And that layer is just it's creating a vector where it's like there's a probability of dog and a probability of wolf for each image, and then it's like it's called a softmax, where it's creating like a distribution where it's like there's an extremely high probability that it's the thing that has the higher probability, and an extremely low probability that it's the other class. It kind of smooths it so it's not a strict maximum. And that's when you get the actual classification. And this is one of those things that it sounds very hard when I express it in language, but it's actually like visually very easy to understand. So I could like quickly share like an article that explains how these works. But yeah, these intermediate representations actually map to real semantic objects in the case of CNNs usually.
You still have to have like, then it seems like you still have to have like this external classification system that's classifying the 1 or a 0 as dog or not a dog or whatever.
Yeah, that's the densely connected layer.
But it seems like the goal of PDP, at least is the way they're suggesting here, is that it can somehow get rid of that, extra, because that's how I was relating. It's like the thing that says whether it's a dog or not a dog, that seems like to be like the English to like learning French, in the sense of
no, that's exactly right, because it's associating like. And you could even think of this as like you're taking an image and maybe like creating a caption or something. It could be like something that's more complex than just a stupid vector that's like a 1 or a 0. And so I think that like what Hinton would say is like this distributed representation is really the learned weights of the model. And so the learning for convolutional neural networks, for instance, happens in these convolutional kernels. You're learning the convolutional kernels. Like you're learning what like low to high level features like the eye of the neural network should pay attention to. And so the actual distributed representation would be the weights. The densely connected layer is more of just, okay, like now that we understand these local representations for given this data, like what choice are you going to make?
Right. Okay, and that's, I guess, where I'm getting caught up is how is that thing then expressing a meaningful choice that isn't then expressed by something else that says this is a dog or this is not, like how does it express something beyond the 1 or the 0? But I think you helped me get closer to. Well,
because it's learning like. So no one has told the network, these are the important features. Like you could create something that's like ELIZA for images where you're like, okay, look out for like something that looks like a doghouse, but it's going to be like horribly painstaking and intensive and very hard to implement. Or you could have something that like, it's able to learn those discriminatory features, and that's distributed representation. And that's a great question.
Thank you so much for everything. Yeah. Especially the recurrence relationships thing. I'm going to have to look into that more.
Yeah. Here, let me just share my email, and you guys should just feel free to follow up. I'm happy to help. if you guys are interested in being directed to more interesting stuff, or if you're like interested in like the programming side of machine learning, please feel free to reach out.
Thank you, Lauren.
Much.
Yeah, thanks again, Lauren. All right. I will see you all in 2 weeks. Have a good, I don't know, I may be going to the thing next week that the New Center is hosting because I'm here in New York. So if you're there, maybe I'll see you. All right. Farewell.
Thank you.
Thank you.
Bye, everybody.
Bye-bye.